Okay, so let's try this log question. We have log base 5, and we have this question here. There's a hidden bracket here. So I want you to think of this as log numerator over denominator. And the rule is that when we have log a over b, this is equals to log a minus log b. So we have to treat this as some fraction, and we can break down the log into two logs. So this here is my top. You have to visualize the hidden bracket here. And so we're going to rewrite this log base 5 xy minus log base 5 of the bottom. Okay, very good. So now we have log x times y. Notice, by the way, how the bases are always the same. When we have base 5, these also have to have the same base 5s. So the other rule now, I'm going to put this in little bubbles here. The other general rule is log, when you have a certain base, I'll just use base 5. You have a times b. It's going to be equals to log that same base, a plus log base 5b. So when you have multiplication for the logs, it gets broken down to a plus sign. And whereas if you have division, it gets broken down into a minus sign there. And in general, if you have a log base c, and these bases will also be base c. All right, so let's finish off this question here. What do we have? We have log base 5 xy, and this becomes log base 5x plus log base 5y. And of course, we just copy down that part over there, which is minus log base 5z. Okay, so what did we just do? We just took this expression here, the original question, and the question was to break it down to individual logs, just with one variable. This is log 5x, log 5y, and then we have minus log 5z. In fact, if the question started off by saying a is equals to log 5x, and the question just started off by randomly saying b is equals to log 5y, and c is equals to log 5z, the question could have said, which would be a bit more challenging, express this original question here in terms of a, b, and c. What a strange question. Express this in terms of a, b, and c given this information. So before you give up, just break it down, and finally we get it down to this format here. And what we notice here is that this here is a, so we have a, so this whole original question here is going to be a plus b minus c. So that is our final answer. Okay, so let's try page 395, example 1b. We have this logarithm here. One of the rules is to convert this radical into a fractional exponent. So we have log 7, and this here is going to be to the 1/3, x to the 1/3. That's what square root would be 1/2, fifth root would be 1/5, and cube root would be 1/3. So another rule about log is that when we have an exponent, we can just drop it down in front. So this here will be 1/3 log 7x. Okay, so let's play with our exponent laws for part C here. We have log 6, and when we have 1 over x squared, that's the same thing as x to the negative 2. Remember, the negative exponent means 1 over that same base to the opposite sign of that. So log rule says you can drop down the exponent, and so we have negative 2 times log 6x. And that is a graph. You can even use Desmos or some graphing calculator to see what that looks like. Okay, so let's try this interesting one. We have log x cubed divided by this business here. And I want you to think about it like there's a hidden bracket here. So log something divided by something. What's the rule? We have log. There's a hidden base 10 here, by the way. It's going to be log numerator minus log that whole denominator, which is y square root z. Okay, so what we have here is we have radical, which is root z, and if you want, you can just not write that at all. It's a good habit to rewrite it as fractional exponents, so I'm just going to get into that habit. So y times root z is the same thing as y times z to the 1/2. And what are the rules here we're dealing with? Exponents, we can drop them like they're hot. And so we get 3 log x minus, and this is where it gets a bit tricky here. We have log something and we have something times something. And I'm going to treat this as something, and I'm going to treat this as another variable. And I can see there's a definite multiplication happening there. So we're going to break it down to a plus sign. Now, very important, we're minusing the whole thing, but the whole thing is going to be broken down to a something plus something. So you must have brackets here. I think this is a common cause of error right here. If you forget the brackets, it's wrong. So what we have is we have log y plus log z to the 1/2. And as you can see, if you were lucky and this was a plus sign, it would have no effect. But the fact that it's a minus sign, we're going to distribute the negative, which completely changes the question. So please be careful. So there we go. I'm just going to write this out one more time here. This is going to be 3 log x. And we might as well just distribute it right now. I'm going to distribute the negative sign here and here. We have a negative log y, and we have a negative, and a positive becomes a negative. And then I'm going to copy this down over here. So you can just copy down over here. This is going to be log z, and I'm about to write 1/2 here, but we know what happens to the 1/2. It gets dropped down, which is 1/2 in front of it. Okay, we're going to simplify and evaluate this question here on page 396, example 2, and we have logs. And notice how these are the same bases. The fact that they're the same bases means that we can actually use log rules. And in this case, we're dealing with a plus sign, minus sign. Really, when you're adding and subtracting, you can move these 3 terms around since addition and subtraction are commutative. But right now, I'm just going to go left to right. I'm just going to focus on these first 2. So I see a plus sign here, and so I'm going to combine it. So we have log base 6. And it used to be something times something got broken down to this. And what are these somethings? They're 8 and 9. So it's going to be 8 times 9. Log a times b is log a plus log b. So we have log a times 9, and that's this part here. This is equivalent to this part here, base 6. And we have minus log 6, 2. So you have a choice. You can either evaluate this. You could say log 6, a times 9 is 72. You could do that if you want. And I will. So we're going to say these are equal. We have log 6, 72. 8 times 9 is 72 minus log 6, 2. And now we have another log rule. When logs are broken apart and have a minus sign, there must have been a division sign before. So what does that look like? Log base 6. We have something divided by something. What were those somethings? We have 72 on the numerator on the left-hand side. And on the right-hand side, we have the denominator, which is a 2. So finally, we have log 6. 72 divided by 2 is 36. Now, please don't stop here. This looks awfully suspicious. We have a log of something is just a number. It's just a number. 6 to the what? There's an equal sign here. 6 to the what is 36? And it's going to be 2. 6 squared is 36, and that's the answer. So this entire ugly statement here evaluates to be 2. Very good. Okay, so let's try another question here. This is on page 396. We have example 2b. And as soon as we see some log statement like this, let's rewrite that radical as a fractional exponent. So what we have is log 7, and this is going to be 7 times 7 to the 1/2. And remember that every number has a hidden exponent 1. And this is where we're going to add exponents. Same base, we have basic exponent laws. We're going to add this. What is 1 plus 1/2? 1 plus 1/2, this is just thinking on the side here, is equals to 2 over 2 plus 1/2, which is 3 over 2. And so this question becomes log base 7, 7 to the 3 over 2. And we're going to drop the exponent like it's hot in front. And so what we get is 3 over 2 log base 7, 7. And the question is, can we simplify further? So I'm just going to circle this part here and be very suspicious. 7 to the what is 7? Very good. It's got to be 1. So this circle bubble here part is 1. So the final answer is going to be 3 over 2 times 1, which happens to be 3 over 2. So just remember that in general, we have log b to the b is 1. Okay, and in general, when we have this kind of notation, we say that b does not equals to 1, because generally it doesn't work. If we say log base 1 to the what is 3, 1 to the what is 3, we can't do that. So we don't deal with bases that are 1. We deal with bases that are greater than 0. Okay, so in general, when we say y is equals to log base a, I'll just use, just a, b, and regardless of what letters you use, sometimes people use b here, sometimes people use c, sometimes people use x, whatever it may be. In general, we say a comma b are greater than 0, must be, and in general, we say the base a does not equals to 1 for the reason we just explained up here. But in general, let me write this one more time. If I say log y equals log base 2 to the x, what does this graph look like? And we mentioned that this must be greater than 0, so we're just dealing with numbers that are bigger than 0 for now. What does this graph look like? What we have here is the x-intercept of 1, and the graph kisses the y-axis, and it cuts through, and it's a dying graph. So it's a dying graph. So when we say here, this value here, x must be greater than 0, visually the log graph, if you memorize the log graph, it's very helpful in remembering the restriction on x, or restriction on b in this example here. It definitely has to be to the right there. All right, let's try this last example here. We have this longer question here using log rules. We're supposed to simplify and evaluate. Notice how these are all base 2. I know these numbers here kind of look messy, but bottom line is if we can somehow combine these all together, we're going to get an answer. So how can we combine them nicely so we're just dealing with nice whole numbers? I'm going to throw the 2 back up, so go backwards. So what we have is log base 2 12 squared, which happens to be 12 times 12 is 144. So 12 squared is 144. That's this business here. And we have a big minus sign and this big massive bracket here. And so we have log 2 base 6. And I'm going to throw this all the way up here, back where it came from. Okay, so we have log 2, and 27 happens to be 3 to the exponent 3. 3 times 3 is 9. 9 times 3 is 27. So that's this 27 to the 1/3. And you can see what happens here. This business here became this over here. 3 bracket 1/3, exponent bracket exponent, we multiply. And so what we have is 3 times 1/3 becomes 1. So essentially this last term here becomes log base 2 3, since these exponents just disappear and they cancel out. So log base 2 3. So I'm going to erase it here. We have log base 2 3. Now the question is starting to look a bit simpler. So I'm just going to recopy this down again. We have log base 2 144. We have minus, and what do we have here? We're going to, this plus this, we're going to have log base 2, this times this. 6 times 3, which happens to be 18. So we have log base 2 18. And finally, we have one last exponent rule. We have a minus sign here. We're just going to rewrite it as division. So use your calculator if you have one. And we're going to say 144 divided by 18 is 8. And please don't stop here. We're almost done. So look here. 2 to the what is 8? And the answer is 3. I'm going to do this one last way. If you don't like what we just did there, we can say log base 2. I'm going to break down 8 to 2 cubed. So literally, we wrote 8 as 2 cubed, and we know the exponent law says you can drop it in front, which is 3 times log 2, and hopefully by now, you memorize that log same is 2 to the what is 2? It's 1. So 3 times 1 is 3. And there's our final answer.